Welcome everyone. Today we shall discuss frequency domain sampling and reconstruction of discrete time signal. Usually it carries 10 marks in the examination and it is very important derivation. Today we shall discuss about it in a simple way. So frequency domain sampling and reconstruction of discrete time signal. So at the starting, discrete time signal is represented by x of n. The frequency domain of x of n is x of e to the power of j omega. That is Fourier transform of x of n is x of e to the power of j omega. So Fourier transform x of e to the power of j omega is sampled and gives a frequency domain x of k. Then we get discrete Fourier transforms. So Fourier transforms is sampled in the frequency domain. Then we get discrete Fourier transform. So we are doing a frequency domain sampling and we get the DFT, and then again we reconstruct the same signal through idft and we come back to the same signal, discrete time signal. Okay, now let us start with a non-periodic discrete time signal x of n. So x of omega, that is x of e to the power of j omega, is equal to summation of n is equal to minus infinity to infinity x of n into e to the power of minus j omega n. So this is the Fourier transform equation. As Fourier transform is not in your syllabus, it is better that you have to remind or we have to remember this equation. Let us consider this as equation 1. X of e to the power of j omega is periodic in a fundamental frequency range of omega between 0 and 2 pi in radians. It is a continuous function. So graphical representation of x of e to the power of j omega is as shown below. Let us consider a continuous waveform, continuous signal, and we will sample. So this continuous signal is considered from the range minus 2 pi to plus 2 pi. So we shall take here the omega. We are considering the frequency omega from the range 0 to 2 pi. So it is greater than 0 and less than 2 pi. So we take n equidistant samples between 0 and 2 pi. So these are the equidistant samples. Here as you can see, we have sampled the continuous signal. So delta omega is width of the each sample. This width of the each sample will be delta omega. The sample space delta omega is equal to 2 pi divided by n. As we know, there are n samples here and the number of samples we are considering is 2 pi. So, the width of the each sample is divided by 2 pi divided by n. So, using this equation, we can replace omega is equal to 2 pi by n into k. So, here for the sample k is equal to 0, that omega is equal to 2 pi by n into 0. So, at the point 0, at the origin 0, the omega will be 0. So at k is equal to 1, omega is equal to 2 pi by n into 1. At k is equal to 2, omega is equal to 2 pi by n into 2, we get 4 pi by n. At k is equal to 3, omega is equal to 2 pi by n into 3 is equal to 6 pi by n. So like this we will get sample 1, sample 2, sample 3 till n minus 1 samples, because we know the range of omega is greater than or equal to 0 and less than 2 pi. When it is less than 2 pi, we have to consider it as n minus 1 samples. So here we get sample 1 at this point, at the origin point. Since k is equal to 0, omega will be 0. At the point 1, when k is equal to 1, this sample will be considered as 2 pi by n. At the next sample will be considered as 4 pi by n. So if we replace omega in the equation 1, we get x of omega is equal to summation of n is equal to minus infinity to infinity x of n into e to the power of minus j omega n. We are substituting omega is equal to 2 pi by n into k. We get e to the power of minus j 2 pi by n into kn, where k lands between 0 and n minus 1 samples. So this is an summation term from summation term where n is equal to minus infinity to infinity. So now, as we know, this is the summation term minus infinity to infinity. So let us expand this summation term here, minus infinity to infinity. Let us expand this summation term. So while expanding, we will get, let us consider here, I have written a small diagram. You can consider minus infinity to infinity. So the summation becomes minus n to minus 1. N is equal to minus n to minus 1 x of n into e to the power of minus j 2 pi by n kn plus 0 to n minus 1. So here from minus infinity to 0, we are considering minus n to minus 1. Then 0 to n minus 1 plus n is equal to n to n minus 1. So all these three terms are in between the summation minus infinity to infinity. So let us consider this as equation 3. Equation 3 is an expanded version of equation 2. Let us write the compact version of equation 3, as we have expanded the equation 2 from the summation minus infinity to infinity. We have got three terms. So this expanded version, let us write a compact version. We have so many summations here, minus n to minus 1, 0 to n minus 1 and n to 2n minus 1. So compactly we can equalize, or we can write a single term or within two terms, that is replace n is equal to n minus ln, then ln is equal to n minus n, ln is equal to 0. If L is equal to 0, then n is equal to 0 to n minus 1. If L is equal to 1, then n is equal to n to 2n minus 1. If L is equal to 2, n is equal to 2n to 3n minus 1. So this means that the expanded version of what you have written, the expanded version of the equation 2, what you have written, so this summation, these three terms, L is equal to 0, L is equal to 1, L is equal to 2. When we substitute these three, here you will get these terms of these three expanded summation. So that means we are summarizing all the summation values and we are introducing a value L so that we can reduce the expanded version summation limits. We are reducing the limits by introducing a L, new letter L. So n is equal to n minus ln. So let us replace in the equation 4. So the compact version will be some x of 2 pi by n into k is equal to summation of L is equal to minus infinity to infinity, and summation of n is equal to ln plus n minus 1 x of n e to the power of minus j 2 pi by n into kn. What does it mean? This means that we are introducing the L so that we can reduce the limits of expanded version. In the expanded version, you have so many limits to consider. To condense it, we are introducing the L. So replacing the equation 4, ln is equal to 0. So here we know that ln is equal to 0. Then we get n is equal to 0 to n minus 1. N minus 1. So rearranging. Now we got the same limits from L is equal to minus infinity to infinity and n is equal to 0 to n minus 1. So here, rearranging the above equation, we will get a summation. The rearrangement is such that we are putting L is equal to minus infinity to infinity this side, so that this term will be recognized as periodic signal xp of n. This term is recognized as periodic signal xp of n. So when we recognize this term as a periodic signal, let us write this whole term as xp of n. So we can write summation of n is equal to 0 to n minus 1 xp of n into this exponential term as it is e to the power of minus j 2 pi by n into kn. So using the Fourier series, any periodic signal can be represented as we know, we have a periodic signal now because this term is represented as periodic signal. Using Fourier series, any periodic signal can be represented as xp of n is equal to summation of k is equal to 0 to n minus 1 ak into e to the power of j 2 pi by n into k into n, where ak is the Fourier coefficient. That will be is equal to 1 by n summation of n is equal to 0 to n minus 1 xp of n into e to the power of minus j 2 pi by n into kn. Consider this equation as 6 and 7. So, the periodic equation which you have done earlier, the periodicity of this signal with this content, this equation is considered as periodic signal. So what you get when you apply this periodic signal as xp of n, you will get a DFT equation. This equation is called as discrete Fourier transforms. That means your signal is already sampled. The Fourier transforms are already sampled in a discrete manner. Then you got this signal. Now using Fourier series, we are going to reconstruct the signal again back. So for reconstructing the signal, you need Fourier series. As we do not have Fourier series in your syllabus, let us remember these two equations for the derivation sake. Comparing the equation 7 and 5, the DFT equation and the seventh equation, you will get AK is equal to, that Fourier coefficient is equal to 1 divided by n into x of 2 pi by n into k. Put the value of AK in the equation 6. So let us consider this equation AK, Fourier coefficient AK equation we will be substituting in the equation 6. By substituting, we will get xp of n is equal to summation of k is equal to 0 to n minus 1 into 1 by n into x of 2 pi by n into k e to the power of j 2 pi by n into k into n. Then again, we are going to rearrange the terms. Why we are going to rearrange the terms? We are going to rearrange the terms so that this constant 1 by n will be taken out. So when we take out this constant 1 by n outside, you will be having an equation like this, which we will consider as equation 9. So equation 9 gives the reconstruction of a periodic signal xp of n from the samples of Fourier transforms. At the starting of the derivation, I told you we are performing a sampling of Fourier transform to get discrete Fourier transform. So now after getting discrete Fourier transform in the equation 5, again we are reconstructing the signal into the periodic signal. That is xp of n is equal to reconstruction the signal using the Fourier series. Then you will get the equation. This equation is considered as idft. So finally, the DFT equation we have got now from the equation 5 and idft equation from the equation 9. IDFT is inverse discrete Fourier transform. We will get inverse discrete Fourier transform by applying Fourier series to the DFT equation. Then finally, inverse discrete Fourier transform will be helpful in reconstructing the signal. Here, omega n is considered as e to the power of minus j 2 pi. It is a phase factor or a twiddle factor. So finally, we have derived at the two equations, that is one is DFT equation and IDFT equation. So this completes the derivation of this frequency domain sampling and reconstruction of DTS. So this carries 10 marks and it is very important for the exam. Thank you.